Okay, good morning everyone. Welcome to Warsaw. This is a warm lecture room. Okay, today we are going to talk about the topics on loss distribution. So first of all, let's see what we are going to talk about, the outline of this clip. In this clip, we're going to talk about the loss distribution, the distribution that's used to model loss. There are seven of them that eight of them that were listed in the textbook with exponential distribution, gamma distribution, normal distribution, Pareto and Generalized Pareto distribution, the Lognormal Distribution, Weibull Distribution, and Burr Distribution. We will have a look each of them one by one, and then after that we will talk about the method of estimation of the parameter. Some of them you may heard of it, like the MLE, like the maximum likelihood estimator. And also we will cover the topic of the method of moment and the method of percentile. And we will again run through each of loss distribution, and then we talk about which method will be appropriate or easy to do with each distribution. After that, we will talk a bit about the goodness of fit test, and then we move on to the mixture distribution, and then we end the clip. The lecture will come along with the problem that relate to the topic that we are talking about. So you can take a note or do a problem along. Okay, so let's start. First of all, let's start from the loss distribution. Okay, I have to say that the content in this book is from the CT6 and mostly from the summary page. Okay, so let's see what we have here about the common characteristic of loss distribution, like what we expect to see from the loss distribution. So when we talk about loss, in this context, we would say about to measure individual claim. That means for individual claim that come into our company, what the distribution will be like, and we would expect to see the positively skewed distribution, or in other words, long tail distribution on the right, because there will be a common loss, like let's say in motor insurance, maybe the just a minor crash is happen like much more frequent than a big one, right? The big crash. So that's why we expect the loss distribution to have a long tail on the right, because there is a chance to have a very high of loss, but that chance is very rare. Okay. Okay, first the cumulative distribution function denoted by the capital F of x. This is just the probability that the random variable x is less than a value of x. Okay, and the density just easily obtained by differentiate the distribution function. Okay, so and here are the list of a distribution that we are going to talk in this clip here. This text tells that these distributions are commonly used to model the individual claim amount. So yeah, after you have the model, right, the distribution, then you have to estimate their parameter. That must be estimated. Okay, maybe the maximum likelihood method of moment or the method of percentile. And then to check the adequacy, you use the goodness of fit. That is one way to do it, or a chi-square tail, in other words. Okay, so let's first begin with the exponential distribution. I think everyone should have seen this distribution before, right? Exponential distribution is a special case of gamma distribution with gamma equal to 1. So exponential distribution only have one parameter, which is lambda, and PDF is given by lambda e to the power of negative lambda x, and here are characteristic of exponential distribution. So this one I crop from the file table. Okay, then let's see this one, the more general one of exponential, which is gamma. Gamma have one more parameter, this which is the alpha here, and this alpha, when it equal to 1, let's see if it equal to 1, you see you will have this one cancel out. Gamma of 1 is basically 0 factorial, and this is also give you the 1, and here if alpha equal to 1, right, this one we cancel out because it will be x to the power of 0. So you will end up with lambda e to the power of negative lambda x, as I said before. Okay, and here are characteristics that list in the table of gamma distribution. Alright, okay. So here's some question to do together here. This one just want us to show that, to verify that the MGF of gamma that given in the table is true. Okay, so let's say x is follow gamma of alpha and lambda. Okay, then if you want the moment generating function of x, you basically calculate the expected value of e to the power of tx, right? And this is equal to the integral form here, you see x is greater than 0, so we have to set the interval from 0 to infinity of e to the power of tx multiplied by fx, which is lambda to the power of alpha, gamma of alpha, x to the power of alpha minus 1, and e to the negative lambda x. Okay, then dx. Then we just do algebra a little bit. So we just let lambda to the power of alpha be the same, gamma of alpha be the same, x to the power of lambda minus alpha minus 1 be the same. And here, since you have base e together, you can just combine it and it will be this one, right? Okay, you will have this one, but what we try to do, we try to find the MTX, right? So we try to set the integrand inside the integral to be another gamma distribution, because that will give us the 1 when we integral over the x from 0 to infinity, right? So if this is gamma, our alpha here will be alpha remain the same, right? But the lambda have to change to lambda minus t, right? In other words, what we try to do, we will doing this. We just take this one out because this one doesn't involve x, right? And then what we want is lambda minus t to the power of alpha. So we have this one, right? And then this one will go to 0, go to 1, as it is gamma of alpha and lambda minus t. Okay, right? Okay, so finally you will have just the one in front of the integral, which is this one. So just simplify a little bit, you will have 1 minus t to over lambda to the negative alpha, okay, which is what we expect to have here. But where does interval the t less than lambda come from? Okay, this one you say that you integral over the domain and reduce it to 1 because this one is alpha, it's gamma of alpha and lambda minus t, right? And we are required to have both parameters to be positive in gamma distribution. So we are required to have the lambda minus t to be positive, which in other words, lambda minus t greater than 0 or lambda much greater than t. And this is what we have, right? Okay, so as you see, you have a nice moment generating function formula for gamma distribution. However, the cumulative distribution function, the df, as you see here, is not a function. It is a function, but it's quite complex. So let's say about finding the p of x less than or equal to x if x is gamma alpha lambda. How do we find this one? I will show you how to use the information in the table. Okay, so what we are trying to do, we just try to use this property. Okay, to do that, you just multiply both sides inside the bracket by 2 lambda. Okay, and as the table say, the 2 lambda x will have the same distribution as the chi-square with degree of freedom to alpha. Okay, so let's say if you say this x is 10, you just open chi-square of degree of freedom to alpha that less than 2 lambda multiplied by 10 or 20 lambda. Or let's say if you want to find the median, you just set the one equal to 0.5, right? And then you look into the chi-square table with you choose familiar with, because we use it so many times, the chi-square table. So you will know that what is the value of 2 lambda x, and later on, let's say if equal to some blank, you just divide both sides by 2 lambda, you will have your x, and your x is basically median, right? Okay, that's about how to using the gamma distribution function. Okay, and here is example. So let's say x is gamma of 10 and 4, and you want want to approximate the probability that x is greater than 4.375. So what we are doing, we have probability of x greater than 4.375, and then if we multiply x by 2 lambda with, in this case, 8, 2 lambda is 8, so y equal to 8x. We will have chi-square of degree of freedom 20, which is double of this 10. Okay, so you will have probability of y greater than 35 because you multiply both sides by 8, and this y is just chi-square of degree of freedom 20. You just look into the table and then you can find the probability to 1 to 5, right? Okay, let's move to the next one. The next one is the normal distribution. The normal distribution is the one that you should most familiar with, sometimes called the bell curve, right? Normal have two parameters with it, mu and sigma square. Mu is just center and sigma square is how spread it is, right? And the most important property of normal distribution is symmetry. How to write it? I'm not sure, but it's symmetric. Okay, so p that x below mu and p that x greater than mu is equal. Okay, so let's see what problem we have here. We want to derive the formula for the moment generating function of standard normal distribution. The standard normal distribution is just normal 0, 1. Okay, so we have set normally distributed with mu equal to 0 and sigma square equal to 1. Okay, so our mgx m, this one will equal to expected value of e to the power of t z, right? And this is the integral from negative infinity to infinity of e to the t z multiplied by since the sigma equal to 1, so we have only 1 over 2 pi with square root, and e to the power negative half of c square, z square, just like this, the z, right? And then we just try to do what we did earlier. So we will have 1 over 2 pi e to the power of 1 over 2 z minus 3 square dz. So this one, what we do here, we have e to the power of negative half of z square, this one and this one, right? We have the middle term, the negative 2zt, and multiplied by the negative half in the front, you will have e to the power of zt here. So we multiply in by e to the power of t square and e to the power of negative half of t square. So we have to multiply e to the power of t square back to make it equal to 1. So we don't make change to anything, to its value. but in the second line this is to 1 because this is a normal of mean t and sigma square of 1, right? Okay, and also the same we have, oh no, we don't have, we don't have the interval constraint, so we just have it equal to e to the power of, oh, I forgot a half. Just this one, and this is the same if you plug in mu equal to 0 and sigma square equal to 1, it's gonna be the same as this one, so this can ensure that we did it correct. Okay, so let's move on to the next one, the Pareto distribution. But before we doing that, we want to wrap up what we did in the last 3 distribution. The last 3 distribution is called by textbook as a basic loss distribution, and the book gives the reason that why they call them like that, because the moment generating function of these 3 functions are in the form of elementary function and quite easy to use. Here, the distribution that I will talk later, in after these 3 we wouldn't have this this easy form, this elementary form of moment generating function. Okay, so the exponential distribution, the gamma distribution, and the normal distribution refer from textbooks as the basic loss function. Okay, then we move on to the Pareto distribution. Okay, so here are the information about the Pareto distribution that we're giving from the table. We have 2 parameters, both required to be positive, alpha and lambda. We have PDF here, distribution function here. Distribution function is quite nice form, right? Moment and coefficient of skewness. Okay, so this one we don't have the problem to do, but we have some example. This one is to show how to find the median of the Pareto distribution. The median is the point where the probability of the value below that point is half or 0.5, in other words. So you just plug in m into the distribution function here and set it equal to a half, and then you solve for m that m is median, right? So we have here, and then we solve for m, we got this one, so we know that m is median is equal to lambda multiplied by 2 to the 1 over alpha and minus 1, right? We got here. Okay, so what the example try to do next is to verify the skewness of the Pareto distribution. So we want to try to compare the mean and the median. Okay, but we have that we look for the same graph, like, and we want to verify that is the mean or median is greater. So we can consider this one as constant because it will set to be some value, right? So instead of we plot the median and the mean, we plot the median over alpha over lambda and the mu over lambda. And here is the graph. Okay, and the graph of mu over lambda is always greater than the median over lambda. So what does this mean by this one? This means the graph is positively skewed, long tail on the right? Because the mean is greater than the median. For those who forgot, I will give you a quick revise. The long tail on the right mean that, okay, let's talk about the median first. The median will be about here, just split into 0.5, right? The median, if we ignore the tail first, so think about the median. First we just ignore the tail. Let's see, we don't see this one. So the median will be here, right? Just around here or here. But when we have this tail, this extreme value, is pull the mean to the right. So the mean will be around here. So that's why we expect the mean to greater than the median when we have the positively skewed distribution. Make sense? Okay. So okay, let's move on. And this one is the generalized Pareto distribution. This is Pareto with one more parameter, the k parameter, and if k equal to 1, this one will come back to be the 2 parameter version. Just that. Okay. So this one we will try to derive the formula for the mean and variance of generalized Pareto distribution, but to save our time, we will try to just show you the mean. The variance will left to be an exercise if you want to. Okay, but it will be the same. I will tell you again what I mean by it is the same. So if you know how to do the mean, you will be easy to derive the variance. Okay, so let's see. So we want the mean of this distribution. We want E of x, where x have the Pareto alpha lambda k, which means E of x is the integral from 0 to infinity of gamma, x first, x multiplied by the PDF, gamma of alpha plus k divided by the gamma of alpha and the gamma of k. And on the top we have lambda to the power of alpha, x to the power k minus 1, and lambda plus x to the power of lambda alpha plus k, right, dx, and x is greater than 0, which we don't have to write because we already include that in the interval for integration. So let's see what will happen if we put x in first. When we put x in, we will have this one remain the same, right, and this one still the same, but x now it will be to the power of k, not k minus 1, and to the power of alpha plus k. So we want this to be another Pareto distribution, but what parameter, right? Okay, let's see. So now at least you can be sure that this Pareto will have k plus 1 parameter, right? Because x is now to the power of k. So what we try to do here is we try to change at least as we can. So as we see, we have alpha plus k 2 times in the distribution. We want this alpha plus k to remain unchanged, which means if k increased by 1, we would try to raise our alpha by 1. Okay, so when we do this one, all alpha plus k will remain the same. So this one will remain the same. We don't have think about it anymore. So do we have to do anything about the lambda? We don't seem that we need to do, right? It don't seem that we need to do, right? Because it is good enough to have the parameter as just lambda. So what adjustment we have to do here? If we have the parameter of alpha minus 1, first of all, this lambda will have to the power of alpha minus 1, and in order to have alpha minus 1, we have to put 1 lambda out in the front. Okay, what else we have to do? We have to change this k to k plus 1 in the gamma function, right? And also we have to change this alpha to alpha minus 1. Get it? So for all adjustment we have done, we have to make it balanced. Right? So everything will be the same. Okay, and this one, when we do this will come to 1 because of what we say here. This is just another Pareto distribution. This is just another Pareto distribution. So finally we will have lambda and gamma of alpha minus 1 divided by gamma of alpha, and gamma of alpha is just alpha minus 1 times gamma of alpha minus 1. So gamma of alpha minus 1 will cancel out and it will left us with alpha minus 1 on the denominator, and on the top, the last term, we will have another k. So this is the formula for expectation of the generalized Pareto distribution. And also the interval, you will see we have this one here, but where does that one come from? That come from the parameter of Pareto distribution required to be positive, as you see here. So when we use the Pareto here in our distribution, each of them required to be positive, which means k plus 1 required to be positive, lambda required to be positive, alpha minus 1 required to be positive, or in other words, alpha is greater than 1. Okay, so for the variance, we just try to find e of x squared, expectation of x squared, and you can derive this one just what we done with the expectation of x. And to find variance of x, you basically just find difference between e of x squared and square of e of x, right? So I will skip that. Okay, so next one is the log-normal distribution. I will break here a bit, just a couple of seconds. Okay, let's go on. The next one is the log-normal distribution. Log-normal distribution have two parameters, just same as normal. We have 2 and sigma square. The PDF is quite a little bit more complex, but it's just a transformation of the normal distribution. The moment is look somehow same as the moment generating function of normal, which is not coincident. We will see later in this example. I will show you. And yeah, all you need to know is log normal means if you take log to the log normal data, it will become normal. Okay, so let's say if x is log normal of mu and sigma square, okay, then y equal to log of x is normal distribution with parameter mu and sigma square. Just simple like that. Okay, so let's see the example here. The example here is they want us to find the formula for average claim amount, or in other words, find the expectation of x where x follow the log normal distribution. So the expectation of x is e to the power of log x, right? E to the power of log x is x, right? E and log can cancel. So, but log x here is y that we state here. And this y is normal distribution. So this one is just the moment generating function with t equal to 1 of the normal distribution. So you will see here that, so in the end, expectation of x is equal to e to the power of mu plus the half sigma square. Okay, and what I want to note here is about how to find how to use the CDF, like how to find the probability of x less than some certain level. Let's say we want x that follow the log normal distribution less than the x. How can we calculate that? The way we do this is we just take log to both sides of the inequality in the bracket, this one. And what we know here, we know log of x, this one is y, and y is normal of mu sigma square. So if we minus both sides, take out mu and divided by sigma, it will become to the standard normal rate, because log x here have normal distribution. So if we apply minus mu divided by sigma to the left, we have to apply the same to the right. So we will have this one. And this one is just a probability from the normal curve. So you'll be able to find that. Yeah. Okay. Okay, so we could then move to the Weibull distribution. Weibull distribution is distribution with this information given in the table, and the textbook give some interpretation of Weibull distribution, so I think it's kind of interesting, so I bring it here. So we say that the loss have the wrong tail on the right, and what we interested about the loss is those extreme loss, especially with the reinsurance. They would like to know about the extreme loss, like the extreme loss, right? And the weight on the right tail can be different. Let's say for the exponential, weight on the right will decay exponentially. Y for the Pareto, weight on the right will decay polynomial, x to the power, right? So exponentially we have a lighter tail because the larger claim will more rare to appear. So what about the Burr distribution? So the Burr distribution, the probability on right tail are given by this expression, which you can see that if you just take the gamma equal to 1, this will be the same weight as exponential, right? However, if this gamma is less than 1, the distribution will be the intermediate weight. So it's not as light as exponential, but not as heavy as Pareto. But if gamma is just more than 1, the tail will be even lighter than the exponential. So you get the idea here? It's just sensitivity of right tail that we try to make it, try to, what we can say, categorize. We take the series fit for the right tail. That's why we have another distribution, the Weibull distribution. So yeah, that's all that I want to bring it up here. And here we want to bring the formula for the mean of Weibull distribution. Okay, let's try to do this one together. So let's say x is for Weibull distribution with parameter c and gamma. Okay, so e of expectation of x, it can be derived as the integral from 0 to infinity of x multiplied by c gamma, x to the power of gamma minus 1 and e to the power of negative cx to the gamma dx, right? Then what we try to do here, we will do a u substitution. We take u equal to e to the power of cx to the power of gamma. We will have du equal to e to the power of cx gamma, and then to apply chain rule, you have to differentiate the one on the exponent. You will have c gamma minus 1 and not gamma minus 1, my bad, c gamma x to the power of gamma minus 1 and then dx. Right? It does seem right. I think we just this one is fine. We take u equal to c to the x to the power of gamma. Yeah, this one seems to be make more sense. Okay, so when we have this one, our integral will change into 0 to infinity of this one will come to du, and this one come to e to the power of negative u. Okay, but we still have x here. What will we do with this x? This x is from this line. You will have x is equal to u divided by c to the power of 1 over gamma. Right? So we just write it here, u over c to the power of 1 over gamma. Okay, then we just apply some geometry, some algebra. We integrate on u, so we try to integrate on u, so the term doesn't involve u can be taken out, which is 1 over c to the power 1 over gamma integral 0 to infinity u to the power 1 over gamma e to the negative u du. And this form is somehow look like the gamma distribution. So we try to complete this one. What we need here, we need alpha, which indicate alpha, lambda, which indicates lambda is 1. So 1 to the power of alpha is just simply 1. And what we have on the denominator is gamma of alpha, and alpha here is this 1 plus 1, because the value that have to go here is alpha minus 1, right? So alpha is 1 plus 1 over gamma, and this integral can come to 1 because this one is gamma of 1 plus 1 over gamma and 1. Then what we did is we add this to the denominator in such an integral. We have to multiply it 2 to make the thing balance. So finally we have gamma of 1 plus 1 over gamma multiplied by 1 over c to the power of 1 over gamma as our expectation. And that's it, exactly what we have if we just plug gamma equal to 1 in the moment formula. Okay, let's move on. Next one, the last distribution that we are going to talk about, the Burr distribution. The Burr distribution is the distribution that have this PDF. This correct. This is how it look like. It looks somehow like Pareto. So I will tell you later what this distribution are from, like how to transform, how to get this Burr distribution by transform the Pareto. Also, I will tell you how to get Weibull distribution by transform from the exponential from or gamma. Okay, from exponential, because I also include the map here. We will talk about it later. So for now, let's have a look at the Burr distribution. The Burr distribution has 3 parameters, which is alpha, lambda, and gamma. All of them require to be positive, and also have the nice formula for the distribution function. This one also quite nice. Yeah, some of them will not have the nice form of the distribution function, but some of them will have. But we will take a note of these nice form of distribution function, and we will see later why we need the distribution function. Okay, so let's see. For the example, we want to find the median for a Burr distribution. So basically we just solve the equation for the distribution function equal to a half. So we solve for x here. If we set it equal to 1 over 2, just like this. And by rearranging, you will have the median here. Nothing much, just algebra work. And then find the median for Burr distribution that for a specified parameter. So we just plug those value in and get the value out. So nothing much. But by having a nice form of our distribution function, we are allowed to find the median or another percentile. It doesn't have to be a 0.5, right? If we want to find the first quartile, for instance, we can just set to 1/4, or if we want to the third quartile, we just set to the 3/4, right? Okay, so let's see about the relationship between the statistical distribution. The one that I highlight is about the one that we have before, the seven distribution that we had before. Okay, let's see. Okay, let's start it with where should we start? Maybe we start with this one. Okay, so the Pareto, the T parameter Pareto, alpha lambda k, when k equal to 1, the distribution will become the Pareto with 2 parameter. The Pareto with 2 parameter, if x is parameter with 2 parameter, x to the power of 1 over gamma will become Burr distribution. So when gamma equal to 1, Burr will become Pareto. Make sense? Or if you want to transform the whole Burr Pareto, the whole Burr distribution back to Pareto, we just transform by x to the power of gamma, and thing will reverse. Okay, same as here for Weibull and exponential, right? So just the same thing, x to the power of 1 over gamma will become Weibull if x is exponential, and exponential is just a special case of gamma where alpha equal to 1. When you take the summation of exponential distribution with same lambda, the distribution of the summation will be the gamma. Okay, so when gamma equal to 1, which means we have only one term of x, it back to exponential. That makes sense. And gamma, if x is gamma, 2 lambda x will become a chi-square distribution, or in other words, the alpha equal to the degree of freedom over 2 and lambda equal to 1 over 2. Gamma distribution is chi-square distribution. For normal distribution, the standard normal distribution, if you take the summation of square of the random variable, the summation will have the chi-square distribution. For normal, mu sigma square and standard normal, this is quite simple. We just transfer like x log mu divided by sigma, or mu plus sigma x. Yeah, depend on which way to go. This one quite simple here. And then about normal and log normal, if you have normal, x follow normal, e to the power x follow log normal. So log normal take log will be normal. Okay, that's all. And because my pen ran out of battery, I have to split the clip into 2 parts. So see you on next part. We will start next part by talking about the estimation. Thank you.